Good day everyone, welcome to Fluid Dynamics tutorial, and in this tutorial we are going to solve or derive the energy of Bernoulli's equation. Before we start the derivation, kindly subscribe to this channel for you to be able to see more of these videos. Okay, now the Bernoulli's or the energy equation is as follows: P1 plus a half rho V1 squared plus rho GH1 is equal to P2 plus a half rho V2 squared plus rho GH2. The parameters with subscripts 1 will be noted as the inlet parameters, that the pressure at the inlet, then the density, the velocity, and then the ones with the subscript 2 are talking about the ones at the outlet, that's the parameters at the outlet. To have more clear view, this diagram shows exactly the type of pipe I'm talking about, whereby we have the inlet area and the outlet area denoted by A1 and A2, then the velocities, then the pressures, and then we have the height of the pipe from the bottom or from the ground level. That's we have H1 and we have H2 at the outlet. Then before we start the solution, there's need for us to define the Bernoulli's equation law. The Bernoulli's equation law states that in an ideal incompressible fluid, when the flow is steady or the flow is constant and continuous, the sum of the pressure energy, kinetic energy, and potential energy remain constant throughout the streamline. That's the summation of all these energies. That's the summation of the energies there at the inlet is the same thing as the summation of the energies at the outlet. So now we are talking about three energies. Let me say total energies is equal to the pressure energy plus the kinetic energy and then plus the potential energy. Let me denote it as this, potential energy. And what are the mathematical expression of all these energies? Let me start with the pressure energy. For pressure energy, we know that pressure is equal to what? Force over area. Therefore, force is equal to pressure times area. When we're talking about the energy, we are actually talking about the work done. And we know that work done is equal to force times distance. Therefore, we are going to say the force, we have it as pressure times area. And instead of the distance, we are talking about the length. So we are going to say the length here. So the pressure energy is denoted as PAL. Let's have a look at the kinetic energy. Kinetic energy, KE, is equal to a half mv squared. Let me denote mass with the flow related variables. We know that mass is the same thing as density times volume. From density is equal to mass over volume. So mass is equal to density times volume. Also, the volume can be denoted as the area times length. We all know this. So now the mass will now be equal to density times area times length. Therefore, the kinetic energy KE will be equal to a half rho AL, then the velocity V squared. Also, let's do the same thing for the potential energy. Potential energy is known to be mass times the gravitational force times the height, that's mgh. In this case, the height, we are talking about the length of the pipe from the ground, from my diagram, which is denoted as z. Therefore, mgz. Also, I have m from the above derivation as rho al. Therefore, potential energy is the same thing as rho al gz. Now I'm going to insert them in the total energy equation, because the Bernoulli's equation law says that the sum of the pressure energy, the potential energy, and the kinetic energy. Now let's sum them up according to the derived expressions. Therefore, the total energy which is equal to the pressure energy. What's my pressure energy? It's PAL plus the kinetic energy, which is a half rho A L then V squared plus the potential energy, which is rho A L G Z. The Bernoulli equation states that the summation of these energies is constant throughout the streamline. That's the sum of the energies at the inlet is the same thing in between the inlet and the outlet, and is the same thing as the outlet. So let me now denote it for the inlet. That's to say P1 A1 L1 plus a half rho 1 A1 L1 V1 squared plus rho 1 A1 L1 G. I don't need to say G1 because the gravitational force is constant throughout. Z1 is the same thing as constant. You can see that I have some parameters that are common in all of the expressions. So now let's reduce the equation to look more beautiful by dividing with the terms that are almost common in every place. So now let me say P1 A1 L1 plus a half rho 1 A1 L1 V1 squared plus rho 1 A1 L1 G Z1 is divide through by rho 1 A1 L1 G over rho 1 A1 L1 G over rho 1 A1 L1 G to be equal to constant. Here this A1 L1 can go this, also this, the density, the area, the length can go, and the same thing here, the density, the area, the length, and also the gravitational force can go. I will be left with P1 over rho 1 G plus a half V squared over G, that's V1, plus Z1 is equal to constant. That is the summation of all these parameters throughout the pipeline is constant, is the same. That's to say the same summation of the parameters at the inlet is the same at the outlet. Okay, let's denote the outlet with the subscript 2. What will this equation look like then? It will then be P1 over rho 1 G plus a half V squared over G plus Z1 is equal to P2, that's at the outlet, over rho 2, the density 2, G, I'm talking about the gravitational force, plus V2 squared over 2G is the same thing as I have V squared over G, then plus Z2. If you leave this as your Bernoulli's equation, it suffices. It's the same thing as the expression given at the beginning of the question. Let's arrange it to be the same as the expression given at the start of the question. That is just to multiply through by rho G. This one or the one above here are all the expression of the Bernoulli equation. Let's meet in the next video to have an example of the problem solved using this equation. But wait, have you subscribed to this channel? If no, kindly subscribe and press on the bell icon so that when we upload the example, you will be alerted. Have a nice day. See you in the next video.